So first thing for today is fraction arithmetic. And the reason we go over this is because one of the first things you're going to learn after test 1 are the derivative rules. And the first derivative rule you're going to learn, one of the first, is the power rule. The power rule just says if you want the derivative of x raised to a power, the power falls down in front and you subtract 1 from the power. So if we have a fraction as our exponent, it's nice to be able to subtract 1 from that exponent. So basically you just have to find the least common denominator, combine the numerators. So I have a lot of examples here where we're just subtracting 1 from something. So 1/2 minus 1. You need a denominator of 2. Nice thing about subtracting 1, it's always just the denominator and numerator are the same. So then it's just 1 minus 2. Keep your denominator. Same thing here. Denominator's 3, so if we're subtracting 1, it just becomes 3 over 3. So 2 minus 3, I got negative 1 over 3. And then 7 over 4 minus 1. My denominator here is 4. So 4 over 4. 7 minus 4 is 3/4. And I called it fraction addition, but that's okay because you're smart enough to know that subtraction is just adding a negative number. Multiplication's even easier. You just multiply the numerator and multiply the denominator and then simplify if you can. So if we have a whole number and a fraction, remember that 2 is the exact same thing as 2 over 1 because every whole number has an invisible denominator of 1. So just multiply the top, multiply the bottom. 2/3 times 4/5. Multiply the tops, multiply the bottoms. Easy enough. 3/4. This time we have a mixed number. So in order to multiply a fraction and a mixed number, we make the mixed number into an improper fraction. So 3/4. 2 times 5 is 10 plus 1 is 11. And then multiply, multiply. WebAssign will be happy with an improper fraction. They do not expect you to turn things back into mixed numbers. And then we have 3/4 and 2 over 15. Multiply numerators, multiply denominators. And this one has a common term. We can write it as 1 over 10. If you like, at this point, you could do some canceling and then you could multiply smaller numbers. 2 goes into 4, leaves me with a 2 down below. 3 goes into 15, leaves me with a 5 down below. And 2 times 5 is 10. So, easy stuff. Let me know if you have questions. Division, invert and multiply. or multiply by the reciprocal. Yes, Christopher.
Just going back to that, just to verify, you can only simplify across, right? Like in an X, like how you did 3 and 15.
And 2, and you could, if you had 3 over 15, you could simplify that.
Okay.
Yeah. Yeah, that's exactly what we did right here. We had 6 over 10, so we divided the 6 into the 60 and ended up with 1/10. So yes, you can, as long as there's no plus signs. That's when you run into trouble. As long as everything's just multiplied here, then you can mark things out and cancel things all you want.
Okay, thank you.
You're welcome. So I'm using the big fraction bar here to represent divide. So this means 1 divided by a half. Again, if you want, you could write that as 1 over 1. But we flip it upside down and multiply. So 1 divided by a half is 2. 2/3 over 5/4 is 2/3 times 4 comes up top, 5 goes down below, multiply across the top, multiply across the bottom. And this last one, I threw a decimal on top. Now your calculator would do that for you. You could plug it in just like that, but I'm going to rewrite this numerator as a fraction. 1 digit after the decimal place means I'm dividing by 10. So we have 25 over 10 times 6 comes up top, 7 goes down below. So speaking to your previous question, I could look at this and rewrite this. 5 goes into 25 5 times, and 5 goes into 10 twice. Then I could look over here and say that 2 goes into 6 3 times. And I'm going to end up with 5 times 3 living on top of 7. Or you could have just multiplied 5 times 6 and gotten 30 over, let's see, what did I miss? 25 times 6. 25 times 6 and gotten 150 over 70. And then simplified that into 15 over 7. So it doesn't matter if you simplify early or simplify later, you'll end up with the same darn thing. Questions about fractions? Okay, good. So you'll be doing lots of fraction arithmetic as you take derivatives. And the reason, because we rewrite radical expressions with rational exponents, which is the next thing we're going to talk about. So first thing we're going to do is rewrite radicals with rational exponents. If you're taking the nth root of x, that's the same thing as x raised to the 1 over n power. If there's no little number there, we assume it's a 2. So square root is x to the 1/2 power. Now, if you have an exponent underneath here, this is x to the m power. So m goes on top, and then the number inside the index of the radical here goes on the bottom. So this is something we can easily take the derivative of. This is kind of intimidating looking. And let's just practice a few. Cube root of x to the 5th power. So the 5 that doesn't really look like a 5, let's make it look like a 5, goes on top. Index goes on the bottom. Same thing if they're reversed. 3 goes on the top. Index goes on the bottom. Now this is a weird one because we have the square root of x to the 1/3 power. It still works the same way. The 1/3 goes on top, divided by the invisible 2 that's right there. So that would be 1/3 divided by 2 is the same thing as 1/3 times 1/2. So this would be x to the 1/6 power. Promise you're going to be glad you can do that. Then the laws of exponents. I know you learned them all, but maybe you haven't used them in a while, so you may be rusty. If we have x to the m times x to the n, well, that's like we have written x down m times, and then we've written x down n times. So how many x's do we have? We have m plus n. Similarly, if we have x to the m sitting on top of x to the n, we have x m times, and then we have x n times. We'll cancel stuff, and we'll be left with x to the m minus n. An exponent in the denominator is the same thing as a negative exponent. So negative exponents just mean, hey, I'm on the wrong side of the fraction bar. So if I have x to the negative n power, that just means x to the n power. If I have 1 over x to the negative n power, that means, hey, I'm on the wrong side of the fraction bar. That's the same as x to the positive n power. And finally, a power to a power. If I have x to the m to the n power, that means I have x times x times x, m times raised to the n power. So that means I have x times x, x times x. So this is m times, and I write it down n times. I end up with x to the m times n power. So those are the rules of exponents. They're true for fraction exponents and whole number exponents. So start with something easy. X squared times x to the 8th is x to the 2 plus 8, x to the 10th power. Square root of x times x squared. is the same as x to the 1/2 times x squared, which is x to the 1/2 plus 2, and 2 is 4/2. So that's x to the 5/2 power. If we have a quotient, square root of x over x squared, I have x to the 1/2 minus 2, which is x to the 1/2 minus 4/4, which is x to the minus 3/4 power, which you could 4/2. 1/2, same denominator, 2 is 4/2. And you could rewrite it as 1/x to the 3/2 power. Either one of those is considered correct. So far, so good?
Yes.
Okay. And let's see, the last one, I have the square root over x squared raised to the 4th power. Well, that happens to be the exact same thing I had here, square root over x squared. So I'm just going to put 1/x to the 3/2 to the 4th power. So that would be 1/x. 4 times 3 gives me 12/2, which is x to the 6th power. Or you could have done it with this one, x to the minus 3/2 to the 4th is x to the minus 6th power. When you're doing your derivatives, if you're asked to take the derivative of something that looks like this, you would rewrite it like this so that you could use the power rule on it. Exponent falls down, subtract 1 from the exponent. So feel a little bit refreshed on fractions now?
Yes. Can you, can you go over the m to the nth power again with the fractions? Go a little bit slower on that.
Which one?
Like that last one you had. Can you do another example like that one? I'm having difficulty like comprehending that.
Okay, so if we have something like x to the 4th over x to the 7th power, and the whole thing is raised to a power, I'm going to make that one a fraction this time. So first thing I would do is simplify the inside. I had already simplified the inside on the other one. So I would start with 4 minus 7. So x to the 4 minus 7 to the 1/2. So that would be x to the negative 3 to the 1/2. And then you just multiply. Negative 3 times 1/2 is negative 3/2.
Gotcha. Okay, thank you.
You're welcome. So after you do all of those derivatives, you're learning the derivative rules, you'll rewrite your radicals with rational exponents, and you'll rewrite your rational expressions with negative exponents. Then you're going to be asked to set those derivatives equal to a number. Maybe you want to know when the rate of change is equal to the rate of change of something else, or most often you're asked to set it equal to 0 because you want to know, no, you don't cry. You want to set the equation equal to 0 and figure out when the derivative is equal to 0 because that's when it has a flat line. And flat lines, interesting things happen, like we have maximums or we have minimums. So we want to know when that derivative is equal to 0. And so we're going to start with something simple because the first thing that we learn to differentiate are polynomials. And when you take the derivative of a polynomial, you get another polynomial. So we need to be able to set polynomials equal to 0 and solve them. So let's start with one that's super simple because that's always my favorite place to start. If you have just a quadratic, you know how to solve it. First thing you do is see if you can factor. Yay, I can factor. Two numbers whose product is 3, whose sum is -4. Let's go with x minus 3 and x minus 1. So x minus 3 is 0 or x minus 1 is 0. So x could be 3 or x could be 1. And the whole thing that makes this work is the zero factor property. Zero factor property says if this times that is equal to 0, then either this is 0 or that is 0. If you multiply two things together and 0 comes out, one of them's got to be 0. It only works for 0. So you have to get 0 on one side of the equal marks in order to do this. That's where students sometimes go astray if they have x squared minus 4x is equal to -3. Then you could factor an x out over here. And if you try setting these equal, you get completely different answers because just because two things multiplied together equal -3 doesn't mean that one of them has to be equal to -3. There's infinitely many x's you could put in there. This case is different. One of them has to be equal to 0. So don't fall into that trap. Let's do another one. 3x to the 4th, 11x cubed equals 4x squared. So I'm going to take my own advice. Get everybody on one side, set it equal to 0, and then hopefully I can factor things out and have a bunch of things multiplied together that equal 0. No, everybody's on one side now. First thing you do is look for a common factor. Everybody's got an x squared. So this leaves me with 3x squared minus 11x minus 4 equals 0. Now, that's not too bad to factor using guess and check, but just for practice, let's do the grouping number method. Grouping number method means we take this number times this number, so the leading coefficient times the constant. That's called the grouping number. And then we ask ourselves, kind of like on the first one, we said, what can we multiply and get 3 that adds up to -4? This time we want to multiply and get our grouping number that adds up to -11. Oh, that's easy. I can use -12 and 1. So I'm going to replace that -11 with -12 and 1. Then I look at each little partnership here. And I look for common factors. Well, I can pull a 3 out here, and I can pull an x out. And I'm left with x minus 4. I look at this little partnership, and they have absolutely nothing in common. But life is good because they look exactly like this little set of parentheses here. So I'm just going to put a 1 next to them. Then I have a common factor, x minus 4 times 3x plus 1, and I have factored it, and I get the exact same thing that I got when I did the guess and check method, just putting down set of parentheses, putting 3x and x, and then I asked myself, well, I need 4 over here. I could try 2 and 2. That's not going to work because that won't give me anything big enough to be 11. So let's try 4 here and 1 here, and I need the 11 to be negative. So I'd put the negative there and the plus there. I don't care how you get it factored, just get it factored. So we have 3x plus 1 times x minus 4 equals 0. So this time we're going to get 3 answers. If x squared is equal to 0, then x is 0. If 3x plus 1 is equal to 0, then x is -1/3. If x minus 4 is 0, then x is 4. Your biggest exponent is the maximum number of solutions you'll have. This one we had a quadratic, and we happened to get 2 answers. This one we had a 4th power, and we have 3 answers, because this one's a double. So far, so good?
Good. So with that you just said, does that mean for each power there's going to be that many numbers of answers?
At most that many, yes.
So what's the rule? Is it 1 less than the power?
Well, no, you can have a 4th degree with 4 answers. The 0 just happens to have what's called multiplicity 2. So it solved this equation twice. X equals 0, x equals 0, then x equals -1/3, and x equals 4. You would never have 5 solutions to a 4th degree polynomial. You could have 4, 3, 2, 1, or none.
Understood. Okay, thank you.
You're welcome. Now let's look at the next one. This one I have x cubed plus 2x equals x squared plus 2. So I'm going to bring everybody over to one side. And you notice as I did that, I wrote it in descending order of exponents, just because descending order of exponents makes me happy. There's nothing wrong with it if you don't do it that way. Now this has 4 terms. My only hope is that I can factor it by grouping. That's the only thing I know how to do with 4 terms. So I look at this little partnership and I look at this little partnership. This one has a common factor of x squared. This little partnership has a common factor of 2. Well, now I have a common factor of x minus 1. So x minus 1 is equal to 0. So x is equal to 1. X squared plus 2 is equal to 0. Well, if I tried to solve that, I would end up with x squared equals a negative thing. That's not going to happen in the real world. So this one we only get one answer. We knew there would not possibly be more than 3. We ended up with just 1. Now this is kind of like the special case. If we have a equation that only has one variable expression in it, then we can isolate that variable and kind of go directly to answer. Use a rational exponent to solve it. Now 5x squared equals 125. So we get the thing with the exponent all alone. Five goes into 125 25 times. So then since I have a squared over here, I'm taking the square root of both sides. X is equal to plus or minus the square root of 25. If you have an even exponent, don't forget the plus or minus. You'll lose half your answers. Yeah, it's easy to forget that plus or minus thing. But remember, negative 5 squared also equals 25. So this could be plus or minus 5. Now, if you think you're going to forget, then don't do it that way. Do it this way. X squared minus 25 is equal to 0. That's a difference of 2 squares. So x is 5, or x equals negative 5. Now, if you have an odd power, it's a little bit easier because it's not a plus or minus thing. If you cube a negative thing comes out. So you only have to take the cube root of both sides. And I needed to adjust this because for some reason I have a negative here, and when I put it over here, it became a positive. So we'll do it both ways. X cubed minus 45 equals 0. Then 7x cubed is 45. X cubed is 45 over 7. So x is equal to the cube root, or 45 over 7 to the 1/3 power, whichever way you like to write it. And if I have it the way I wrote it in the other little box there, plus 45, then I have 7x cubed is equal to the negative of 45. So x cubed is negative 45 over 7. So x is the cube root of negative 45 over 7, which is the negative of the cube root of 45 over 7. Those have a perfect cube. Now, if you really want to, you can factor a sum or a difference of two cubes, and you'll always only get one real answer. You get one real answer and two imaginary answers. But you can just take the cube root of each side. Much easier. X to the fourth minus 81 is equal to 0. I'll add 81 to each side, and then I take the fourth root of each side. Or you can think of raising it to the 1/4 power, because remember, a power to a power means that we multiply, and 4 times 1/4 leaves me with just x to the first power. And this is going to be plus or minus, put a little plus or minus in there, the fourth root of 81. 81 is equal to 3 times 3 times 3 times 3. So that's plus or minus 3. Now, maybe you looked at this and you thought, hey, that is also a difference of two squares. I could write this as x squared squared minus 81. So it would be x squared minus 9 times x squared plus 9. And this is a difference of two squares, x minus 3 times x plus 3 times x squared plus 9. So x is equal to 3, x equals negative 3, and this one has no real solutions. So we still end up with just those two answers.
I have a question.
Okay.
So why x squared plus 9 doesn't have any solutions?
So if you isolated x squared plus 9, you would have to subtract 9 from each side. It has solutions, they're just not real.
Okay.
So it's plus or minus 3i. In calculus, for the most part, and especially in Calc 1, we're only going to be looking for the real solutions. It does have solutions, they're just not real.
Thank you.
You're welcome. And what do we do when the quadratic equation doesn't factor? Well, then we have to think way back and do the old familiar quadratic formula. Quadratic formula will always work if you don't like to factor or you just have a brain freeze and can't factor. X squared minus 4x plus 3 is equal to 0. So A, B, C, negative B, plus or minus square root, B squared minus 4AC, B squared minus 4AC, all over 2A, all over 2A. Yes, you have to hear that song again. So negative B plus or minus square root B squared minus 4 times A times C all over 2 times A. Negative 4 is 4. 16 minus 12 over 2. So 4 plus or minus 2 over 2. So 4 plus 2 is 6 over 2, which leaves me with 3. And 4 minus 2 is 2 over 2, which gives me 1, which is the same thing we got when we factored it. So if you can't factor, your brain goes, you can always use the quadratic formula. You may have something that doesn't factor easily into nice friendly numbers. Something like x squared minus 2x minus 5 equals 0. And so you think to yourself, I don't know if this factors or not. I'm going to just plug it in to my calculator. And let's clear. There we go. Clear out of that. Let's go to the polysolve button. So in this one, A is 1, B is negative 2, C is negative 5. So 1, negative 2. Oh, negative 5. You'd think I'd already done this problem today. I guess, yes, I have. So solve that. And oh, I get these big long numbers. And WebAssign said it wanted an exact answer. So darn, I can't put in negative 1.49489743 because WebAssign's going to give me that ugly red X mark instead of the happy green check mark. So I have to go back to negative b, a negative of negative 2 plus or minus square root b squared minus 4ac all over 2a, which gives me 2 plus or minus, let's see, it's 4, negative times a negative is a positive, so 4 plus 20 over 2, which is 2 plus or minus 24. You think about what's the biggest perfect square that I can divide into 24. Well, that would be 4. So I have 2 plus or minus 2 times the square root of 6 over 2. 2 goes into 2 once. 2 goes into 2 times the square root of 6. Leaves me just square root of 6. Now, another thing that your calculator does for you, which you may or may not know, is it rewrites your quadratic here in the form of a times x minus h plus k. Get rid of that one, we'll get a new one. So a times x minus h squared plus k equals 0. So it's writing it in vertex form. I already know my a is equal to 1 in this case. It tells me what h and k are. H is equal to 1, so x minus 1 squared plus k is equal to negative 6. Well, now I have something I can solve. This is x minus 1 squared, add 6 to each side, is equal to 6. So x minus 1, that square root property, and don't forget the plus or minus, is equal to plus or minus the square root of 6. So x is equal to 1 plus or minus the square root of 6. So your calculator is still your really good friend. even though it gave you those big, long, nasty decimal answers, you can still use it to get to that final exact answer that WebAssign wants. Questions?
Wow. Is there any way to have, because I know that you could do it with fractions where you can have it go back and forth between the fraction or the decimal form. Is there a way to have it, I guess, kind of put it in that form? Or
No.
you have to solve the formula, right?
Yeah.
Okay.
It's not that smart. I wish it were. It's not that good. But at least that's not too bad. You can use that little shortcut there.
Yeah, that's definitely a lifesaver if I'm stuck.
Now, let's look at this last one here, where we end up with only imaginary answers. The way that you know that you're have no real solutions. Let's get out of here and we'll start over again. Second, polysolve. Same, let's get rid of that one. I was really unimaginative just putting in x squared plus x plus 1. As soon as you see that your answer has this plus sign here, you know there's an I sitting there at the end, so you know that there's no real solution. Which means this one has no zeros in the real world. It never crosses the x-axis. That parabola, it's a happy parabola, so it's sitting above the x-axis somewhere. So feeling a little better about solving polynomial equations.
Yes, definitely.
Your calculator will solve cubics for you, but nothing any bigger than that.
One question for you.
Yes.
On that last one, if you were to, like, I guess, so I'm looking at that bottom problem, and then when it goes from that second to last equation to where you add the I, is that the step where you're pulling the negative out, I guess?
Yes.
The -4, okay.
Yeah. Yeah, anytime you have a negative under a radical, as I used to tell my 171 student, you have to pull your eyes out. It sounds really painful, but it's not. It's just pulling that little I out in front of the radical.
Got it. Thank you.
Okay, last thing we're going to talk about is solving exponential equations, because you're also going to learn the derivatives of exponentials. Is one of the first things you learn. So you'll be setting those equal to things as well. Some things to remember. Rules about logarithms, because logarithms are what we use to solve exponential equations. Log base A of x is equal to y. What does that mean? That means that a to the y power equals x. That's how I remember it. I draw a little loop. So if I have the log base a of a equals 1, because a to the first power is equal to a. Log base a of 1 is equal, log base a of 0 is equal to 1. Because, I had it right the first time. Log base a of 1 is equal to 0, because a to the 0 power equals 1. Everything to the 0 power equals 1. And the other things you need to keep in mind is that log base a of b is just a number. If you plug it in your calculator, if A's and B's are constant, you just get a number out. It's a long number with lots of decimal places after it. But for example, log base 2 of 3. This would be an exact answer that would make WebAssign happy if you were asked for an exact answer. If you plug log base 2 of 3 into your calculator, so let's get out of here. To get log base 3 of 2, you hit this log button 1, 2, 3 times, and then that little subscript appears, and you can put log base 2 of 3 in there and get a long decimal number. 1.58496. This is an approximation. So if WebAssign asks you to round it to a certain number of decimal places, then yes, you plug it in your calculator. But this is just a number, and we treat it like a number, and we feel really good about ourselves because we've gotten an answer when we get there. And the other thing is the change of base form. Log base A of B is equal to the natural log of the input divided by the natural log of the base. So if we have an exponential equation, first thing we try to do is get that exponential expression all by itself. Anytime you have a number raised to a function, you can solve it by using log base whatever that number is, or you can solve it using natural logs. You can always solve everything using natural logs if you want to. If we wanted to solve it using log base 4, we throw logs at both sides. So I threw log base 4 at both sides. One of the laws of logarithms says that this exponent here can fall down in front. That's the thing that we love about logarithms. That exponent can fall down in front. So now I don't have a variable in the exponent anymore, and I'm really happy. Now, the reason I chose log base 4 is because log base 4 of 4 is equal to 1. So now I have this nice friendly 2x plus 3 is equal to log base 4 of 5, but I remind myself that's just a number. It's a funny looking number, but I'm going to treat it just like I would any other number. I can subtract 3 from it, and I can divide it by 2. And now I have my answer, my exact answer. Now, some people don't like using log base 4. They want to use natural logs to solve everything. If I want to use natural logs, 4 to the 2x plus 3, I can throw natural logs at both sides. 2x plus 3 still falls down in front. Natural log of 4 is just a number. Natural log of 5 is just a number. Divide, divide. Oh, look at that. Natural log of 5 over natural log of 4 is equal to log base 4 of 5. It's exactly what we had over here. So I'm getting the same darned answer. It just looks a little different. They're both perfectly good, exact answers. So if you like using log base 4, then use log base 4. If you're a big fan of the natural log, then go the natural route and do that. Questions?
Can you show me how to use the calculator again? It was log 2 something.
So you press the log button 3 times, and then the little place comes so that you can put your base in there. So if I wanted log base 4 of 5.
So if I hit the 3 times and it's show me log base, it's just like a,
Yes.
yeah, and then I cannot put the number to the base section,
Yeah, you put a number in there.
but it's not, I can't do that on my
You
calculator.
can't?
No.
Do you have a calculator like this?
Yes, it's the same calculator, but when I tried a couple of times, but it's just show me like a log base. Like literally it's show me like BASE.
Huh. Go to your mode.
Uh-huh.
Let's see. Maybe the last thing may be different. Do you have classic or do you have math print?
It's classic.
Okay, switch over to math print.
Okay.
And
Yep,
now,
got it. Thank you.
you're welcome. All righty, let's do some more. Now, the next one we have E. So it's the natural exponential function. So we would definitely use the natural log to solve this. Let's see. So we have e to the x plus 4 plus 6 is 29. So just like before, we isolate that exponential term. So subtract 6 from each side. And that is an x plus 4. And then we throw the natural log at each side. And because I get lazy, I'm just going to go ahead and do it right here. X plus 4 falls down. I have the natural log of e is equal to the natural log of 23. Natural log of e is just like the log base e of e equals 1. So x is equal to the natural log of 23 minus 4. Easy peasy. Next one just adds one more little step to it. And let's see, I think that's a minus 7 plus 1 equals negative 59. So just like if you had minus 4x plus 1, First thing you would do would be to subtract 1 from each side. Next thing you would do is divide both sides by -4. And -4 goes into -60 15 times. So then you would throw logs at both sides. And 22x minus 7 would fall down. You'd be left with natural log of e, which is equal to 1. So 22x is equal to the natural log of 15 plus 7. And divide both sides by 22. Oh, that was supposed to be 2.2. So questions?
The 2.2, are you saying from the whole beginning of the problem? Or
yeah, it was supposed to be 2.2 from the very beginning.
I thought there was some rule with the logs. I was like,
no, there's not a rule. It was just that my eyes are old. And it was supposed to be 2.2 from the get-go.
I couldn't see it either, so.
Oh, okay. Well, then we'll just say it's 22 and leave it as 22x natural log of 15 plus 7 over 22. Yeah, it's whatever number is there. It's no magical, mystical thing that you have to do special. It works just the way dividing both sides by the number sitting next to x always has. Now, this next one's funny looking. This one has x's and e to the x's in it. And it has a bunch of e to the x's in it. So really, I can't isolate that e to the x the way I did the others. So I'm going to go back to what I did with polynomials and get everybody on one side of the equal mark. Now, x squared e to the x minus x e to the x minus 6 e to the x equals 0. Oh, looky there. Everybody's got an e to the x in it. So let's just factor out e to the x. How convenient. Life is good. That thing factors. Two numbers whose product is -6, whose sum is -1. So e to the x could be equal to 0. X minus 3 is equal to 0. X plus 2 equals 0. So off the top of your head, when does e to the x equal 0?
Never, right?
Never. It never equals 0. E to the x looks like that. I don't draw very well, but I can draw e to the x. It looks like that. It grows really fast and it gets closer and closer and closer to 0, but it never gets there. So this one has no solution. Even if you try to solve it by taking the natural log of each side. What happens when you try to take the natural log of 0? Even your calculator gets mad at you. No solution. So as soon as you see that, you can put a big X through it. You do get two perfectly good answers. You get X equals 3 and X equals -2. Okay, we got another one. Looks kind of like a polynomial. We have e to the 2x minus 3e to the x plus 2 equals 0. So it looks kind of like a polynomial, except instead of x's, we've got e to the x's. What if I let u be equal to e to the x? Then u squared would be equal to e to the x squared, which we learned earlier means multiply those exponents, e to the 2x. So what I have here is u squared minus 3u plus 2 equals 0. Yay, I can do that. Two numbers whose product is 2, whose sum is -3, minus 1, minus 2. U minus 1 is 0, u minus 2 is 0. But u is equal to x squared. X squared minus 1 is 0. E to the x. E to the x minus 1 is 0, or e to the x equals 1, or e to the x minus 2 is 0. So e to the x is equal to 2. And now you take the natural log. Natural log of e to the x is x. What's the natural log of 1? Oh yeah, it's 0 because e to the 0 power is equal to 1. Or natural log of e to the x is x. So you get two nice, friendly, exact answers. Got another one, kind of like that. E to the 4x, and I'm going to go ahead and write everybody over on one side of the equal mark. So minus 21 is equal to 0. Now I see that this is 2 times this exponent here. So I'm going to let u be equal to e to the 2x. Then u squared is e to the 2 times 2x, 4x. So I have u squared plus 4u minus 21 is 0. Now, if you're really comfortable with it, you don't have to go through the steps of sticking those u's in there. I'm going to go ahead and factor. So plus 7 minus 3 is going to work for me. So u plus 7, in other words, e to the 2x plus 7 equals 0. Or e to the 2x minus 3 equals 0. E to the 2x equals -7. Well, as soon as you see that, you're dubious. You think, is there anything that I could raise e to and get a negative thing to come out? I know that e to the x looks like that. It never goes down below the x-axis. And if I tried to take the natural log of both sides, I'd be trying to take the natural log of a negative thing, and that can't be done. Big X mark. E to the 2x equals 3. Oh, now this I can do. Natural log of e to the 2x is 2x. Natural log of 3, so x is equal to the natural log of 3 divided by 2. I get one answer. Questions?
I have a question. All the time, I'm so confused. It's exponential equations, especially like natural log things. So what is a natural log exactly?
The natural log is log base e, and e to the x is just a number. E is equal to 2.71 ... It goes on forever. So e to the x is just a number raised to a power. Natural log of x is equal to log base e of x. So log base e of x means that e to the y is equal to x. So they are inverse functions of one another. I'll graph them on Desmos because that'll look a lot better than if I sketch a graph. Okay, that's not going to let me open up a window. There's Desmos. It's beautiful and it's free. So there's e to the x and then natural log of x. There's the identity line. You can see that they're inverses of each other because they're reflections about that identity line. So e raised to the 0 power is equal to 1, so the natural log of 1 is equal to 0. E raised to the first power is equal to e, so the natural log of e is equal to 1. Did that help?
Yes, very, very much. Thank you.
You're welcome. And where e comes from is the limit as n approaches infinity of 1 plus 1 over n to the n power. The way I've always explained it is when people were doing compound interest, they wanted to keep compounding the interest more and more. Well, I'm going to do it every day. I'm going to do it every hour. I'm going to do it every minute. So they let the number of compounding periods approach infinity so that you're continuously growing and you end up with E, and that's where the PERT formula comes from, which you may remember from pre-calculus. That's where E comes from. You shouldn't ask a math nerd a question about a number. Last one we have here, e to the x minus 12 e to the negative x. And think of this one as a challenge problem, because this one's challenging. It looks kind of like those others that we did. We have an e to the x, but we have an e to the minus x. So this is really e to the x minus 12 over e to the x minus 1 equals 0. So I'm going to put that minus in the middle. And then, oh, that one's a minus 2. So minus 12 over e to the x equals 0. I want this to be something squared. Well, if I take x to the 1/2, then u squared is equal to x to the 1/2 times 2, so that would be e to the x. So then this e to the negative x would be equal to u to the minus 2. So I could let u be equal to x over 2. I'm going to have u squared minus 1 minus 12 over u squared equals 0. This I can factor as u minus, I need two numbers whose product is negative 12, whose sum is negative 1, just like I've always done. So this would be minus 4 and plus 3. And if I put a u on the bottom, when I do first times first, I get my u squares. When I do outers, my u's cancel and I get just the 3. When I do inners, my u's cancel. I get just minus 4 and I get that minus 1 that I need in the middle. And when I do last, I get 12 over u squared, exactly like I need. So it's a little different. Not just a polynomial like we've had before. But now I can take each of these little pieces, u minus 4 over u equals 0, or u plus 3 over u equals 0. And now I'll replace u with x over 2, e to the x over 2. And I'm going to get things on opposite sides of the equal mark because I'm a big fan of cross multiplying. When I cross multiply, I'm going to put my 1 on the bottom there just so this one has somebody to play with. E to the x over 2 times e to the x over 2 is e to the x. 1 times 4 is 4. And now finally, it looks easy. Natural log both sides. X is the natural log of 4. I'm going to try the same thing over here. U is equal to e to the x over 2 plus 3 over e to the x over 2 is equal to 0. So e to the x over 2 is negative 3 over e to the x over 2. Invisible over 1. Negative 3 is equal to e to the x over 2 times e to x over 2. Add the exponents. No solution. So we get one good answer.
Professor, I have a question there.
Yes.
So when you are on the right side there, why don't you apply that negative sign to the e to the x in the denominator?
Over here, I gave it to the 3. There's only one minus sign, so you could give it to the 3 or you could give it to the e to the x.
Okay. don't know why, but mentally I always thought that it applied to both of them.
No, because if you had a minus over a minus, that would be a positive.
That makes sense. Okay.
Yeah. You only have one minus sign, so only one of them gets to be negative.
Thank you.
Yep, you're welcome. That was a hard one, so if that one kind of blew your mind, don't feel intimidated. It's okay. Questions?
No, thank you so much. It helps a lot.
Good. And I do need you to do this silly survey. So let me pull up the link for the post survey.
Okay.
And I'll send it out to the other people who left. That's how they justify having the boot camps, is when you say, oh, yes, I feel much better about things now.
Yeah, these are extremely helpful.
Good, I'm glad.
Is there anywhere to put like requests for different topics?
In my brain, just ask me. What would you like?
Is it possible to do one on using the calculator properly? I feel like that's something that I've just been kind of thrown into and don't really know how to properly use the calculator.
Okay, I try to throw those in as I do it, but yes, anytime you have a calculator question, please ask me. I'm happy to help you use this calculator because it's freaking awesome.
Yeah, that's what I keep trying to find like guides online that are just like basic tips and stuff. And I just found the PolySolve one yesterday.
Yeah.
I never knew that was a thing, and then I found that. So I'm just trying to see if you could do like a general overview, maybe not like a whole boot camp, but like a small class on general
Okay.
overview of using the calculator.
Maybe I'll like do a tip a week or something on using your calculator. Yeah, that's a good idea.
That would
Sure.
be awesome.
Yeah.
And do you have boot camp like every Friday or?
Yes.
Okay, gotcha.